So we should have time today at the end of class to talk about one homework problem I want to discuss quickly. But for today, we'll keep moving on. Well, for now, we'll keep moving on anyway. We had the angular form of Cheva's theorem last time. Today I want to move in a slightly different direction, but use angular Chevas to prove important results here. And what I want to do is define the sixth triangle center. Right, so in Kimberling's list in his encyclopedia of triangle centers, we've talked about the first five. Right, we've got the in-center, the orthocenter, in no particular order. I believe in-center is number one, but after that, who knows? In-center, orthocenter, centroid, circumcenter, 9-point center is the first five. And then we discussed something, if you recall, the Gergonne point. That's number 7 in his list. So we skipped number 6, which is the Samedian point, or the Lamone point. And I'd like to define that today. And the way I want to define that is it's very easy to define it if you know what these words mean. The Lemoine point, or the Samedian point, is the isogonal conjugate of the centroid. The problem is, you guys don't know what isogonal conjugates are yet. So, that's where we need to start. We need to build up terminology. I want some colors today. Get my colors. And this will be a little bit, we've got to first talk about isogonals, Samedians, and then finally isogonal conjugates. So there's a little bit of work to do here, but we'll take triangle ABC, as we always do. And I'm going to drop in the angle bisector. I'll just, I think we can go with a solid line. Let's pretend AX looks also like a median because my triangle looks very equilateral, but AX is the bisector of angle A. And AP is any Chevian. Here I've drawn an interior one. So AP is any Chevian. What I want to do is I want to reflect it. I want to reflect AP through this bisector, through AX. So let's let AP prime be the reflection of AP in the angle bisector AX. So I'm taking AP and I'm reflecting it through AX to get another Chevian, AP prime. This is another Chevian, known as the isogonal of AP with respect to this triangle. So known as the isogonal of AP. And usually that's all you have to say. It's clear what triangle you're working with, but if you want to be very formal, it's with respect to triangle ABC. I haven't used WRT much this semester because we haven't had to, but it's so common in mathematics that people usually abbreviate it with respect to. What do I mean by reflection? When I say reflection, what am I preserving here? Well, the name might actually give you a hint. Iso in is it Greek or Latin? I believe it's Greek. Iso meaning same, and gonal referring to angles. So it's the angles that are preserved. So this angle here is the same as this angle here. And so angle PAX is the same as angle P prime AX. the important thing. Any questions? All right, so nothing too fancy so far. That's all isogonals are. You take your Chevian and you reflect it through an angle bisector. Well, the angle bisector that originates in the same vertex your Chevian does. And there's nothing special about interior Chevians here. I could have gone exterior. Haven't left myself a whole lot of space, but probably should have gone a little bit closer. But there's AQ. If I look for its isogonal, well, this exterior Chevian would reflect to an exterior Chevian over here. So AQ prime is the isogonal of AQ. Just another example drawn there. And once again, that means that this angle QAX is the same as Q prime AX. So if I was going to write one theorem right now based on isogonals, what might I state? Well, you'll notice that the isogonal of an interior Chevian in this drawing gave me an interior Chevian, and the isogonal of an exterior Chevian gave me an exterior Chevian. Can you see that that's always going to be true? Right? Why was this one interior? Well, because the angle here had to be the same as this angle, and since this is a bisector, this angle is strictly bigger. I don't want to keep saying this, but I don't want to phrase this. Right? I've got this smaller angle inside of a bigger angle. The angle over here is the exact same size, so if I'm trying to fit that smaller angle over here, of course it's going to fit on the inside. Right? Something along those lines, if you can see that. Very loose argument. But we'll just make a note, right? We don't want to prove this. It's really quite obvious. But note, Chevian is interior if and only if its isogonal is interior. Can you guys see that? I feel like I very badly botched why this is true, but the argument. But can you see? Is everyone comfortable with that? Yeah. Okay. And of course, the contrapositive here that I'm not stating would be a Chevian is exterior if and only if its isogonal is exterior. So I suppose I could have fit this in words here. I could have said a Chevian is interior or exterior if and only if its isogonal is interior or exterior. All right, so first theorem I want to prove is about concurrence of Chevians and their isogonals. And it's a really big deal. It's sort of the first fundamental fact about isogonals. And what I'd like to prove or claim, what I'd really like to be true is that if I have three concurrent Chevians, then their three isogonals are also concurrent. Problem is that doesn't always happen. But what does always happen is the three isogonals are concurrent or parallel. So I won't state as a theorem, because it's actually a corollary of the Angular-Cheva's theorem. Corollary of Angular-Cheva. And it says the following. It says if Chevians AP, BQ, and CR of triangle ABC concurrent. Well, I suppose it's also true for parallel, not just the isogonals. So if they're concurrent or parallel, then so are their three isogonals. And their isogonals are also concurrent or parallel. So I call this a corollary, meaning it should follow, the proof should follow fairly easily and then quickly from our Angular-Chapis theorem. And what am I assuming? I'm assuming that I have three Chevians that are concurrent or parallel. So let AP, BQ, CR be three concurrent or parallel Chevians of triangle ABC. Not current, concurrent. What do I know by Chapis theorem, or Angular-Chapis theorem? If you're concurrent or parallel, then the angular Chevian product must equal 1, and an odd number of them must be interior. Okay? So then, an odd number of them are interior, either 1 or 3, and let's say there. For them, their angular Chevian product equals 1. My claim is that this is also true for the isogonals. Why is it true that an odd number of the isogonals are interior?
Because if any Chevian is interior, then it's isogonal.
And its isogonal is interior, right? It's the note we just had. So as we look at the isogonals, the number of interior versus exterior Chevians, or isogonal Chevians, isn't going to change. So by the previous observation, an odd number of their isogonal Chevians are also interior, because you can't change from being interior exterior. And I claim the following. I claim that if you take the angular Chevian product of the isogonals, it's going to be the reciprocal of what we started with. And I don't want to write down too many details here, so I'll just say it's not hard to see. We'll discuss in just a second, and it's not hard to see. Very lazy proofwriting, by the way. Don't ever do this on homework or anything, but you'll see this in textbooks and published proofs all the time. It's not hard to see that the angular Chevian product of the isogonal Chevians, the isogonals, is the reciprocal of the original nice thing about 1 is that the reciprocal of 1 is also 1. And therefore, also equal to 1. Why is that? So, let's say I have a Chebbian, and then it's isogonal. There's its reflection. What do I start off by doing? In my original angular Chebbian, I take sine of this angle over sine of this angle. Right? Well, if you think about how reflections work, then you'll notice that this angle right here is exactly the same as this angle right here. So for the isogonal Chebbian, I take sine of this angle, which is actually sine of this one, the guy in the denominator, over sine of this bigger angle. But that's exactly the same as this bigger angle here. So you just have to think about reflections and what the angles actually are, but it is indeed the reciprocal for each particular Chebbian. So that's not hard to see. And therefore we are done, right? Go back to angular Chebys theorem. Because for the isogonals, an odd number is interior, odd number are interior, and its angular Chebbian product equals 1, then they must be concurrent or parallel. So hence, by angular Chebys theorem, the isogonals are concurrent or parallel. And unfortunately, the cases don't match up. If they did, I would have stated that. I would have said if they're concurrent, if you start off being concurrent, then the isogonals are concurrent, and if you start off being parallel, then the isogonals are parallel. They don't necessarily match up. So 3 concurrent Chebbians can correspond to 3 parallel isogonals, and vice versa. But that is a hugely important theorem as we go through this stuff, that concurrency of Chebbians and their isogonals sort of correspond. And with that, I can define the median point right now without even talking about isogonal conjugates, so we'll get there. But let's let's do 3 particular very important isogonals. So once again, do I need a picture? Probably don't need a picture here. What are 3 very important Chebbians? The medians. So the isogonals of the medians are usually given names. They're the symmedians, which is short for symmetric medians. So the isogonals of the medians of triangle ABC are called the symmedians. Of triangle ABC. And why sim? Again, think of this as being short for symmetric medians. What do we know about medians? We know medians are concurrent, right? They're concurrent to the centroid. So because medians are concurrent at the centroid G, it follows from the previous result, from the previous corollary, that the symmedians are also concurrent. How do I know they're concurrent and not parallel?
So the Chevians are interior.
Yeah, right. We start off with 3 interior Chevians, so they're isogonals. The symmedians must be interior, and 3 interior Chevians can never be parallel. So exactly. So we'll just make a note here. They cannot be parallel. Because they are interior. And their point of concurrence is called the symmedian point. Their point of concurrence is called the symmedian point. As I understood, this point has a few different names because it was sort of independently written about by a few different people. Apparently, as I understand, this name is a little bit more common in sort of this side of the world, in America. Over in Europe, it's usually given the other name after one of the French mathematicians that discovered it. My French is terrible, I might be butchering his name, but the Lemoyne point. This is triangle center number 6 in Kimberling's list. So now we have 1 through 7. Do I want to try drawing it? Let's try to draw. There might be way too many lines here, and my drawing might be way too off of being accurate to make any sense, but we can try. And so, I start with a triangle. Shame that line's not straighter. ABC. Let's try to dot in the angle bisectors here. So, what looks like an angle bisector? About that. There's my bisector. There's my bisector, and this guy has to go through this point because I know they're concurrent. So I'll start with the incenter and dash out from there. There's my 3 angle bisectors. And the problem I'm running into here is that my medians look a whole lot like the angle bisectors, but roughly halfway down this line. What do you say it's about here? Is that about the median? Yeah, sure. There's a median. And I want to reflect it. I want to reflect it through this angle bisector to get the symmedian. right, let's try that again. Let's do another median. Halfway down this line AC, this line's not very straight, but maybe about there. Draw on this median. And we'll reflect it to get the sim median. This kind of sucks. I'm going to have to adjust my drawing a little bit here. Otherwise it's not going to look quite right. Let's take my bisector and draw it slightly down there. There we go. Okay, so now I take the median from A. My bisector is not exactly a straight line, looks like it curves a little bit, but my median should pass right through here. This is the centroid. So we'll pass the median through there. And if we reflect it over, by our result, the sim median should pass right through this point of intersection because they have to be concurrent. So there we go. This point here is the sim median point. And this point here is the centroid G. And if you want, this point right here, the intersection of the three angle bisectors, that's the incenter I. So there's a lot of lines drawn on this triangle, but the construction itself isn't hard. The problem is once you have all the lines on there, it starts to look a bit messy. But that's the definition of the median point, the construction of it. Any questions? Okay. Yeah, really important point in geometry. We won't talk much about it though, really at all, but it's nice to define this, so now you know what the first 7 triangle centers are. What I want to do is keep moving on, which is, again, my definition, the median point is the isogonal conjugate of the centroid. So let's talk about what isogonal conjugates actually are. So given a triangle ABC, let X be any point in the plane not on the lines AB, AC, or BC. Be careful with the reading here. I'm not talking about the line segments. I'm not just talking about the line segments that make up the triangle. I'm talking about the lines, so extend these infinitely. Sometimes people just call these a nice descriptive name. Extend all the lines of the triangle. They call these the sidelines of the triangle. And what I'll note is that if I connect vertices A, B, and C to X, I have 3 Chevians. 3 Chevians that must be concurrent at X. So AX, BX, and CX are 3 Chevians. Three Chevians of triangle ABC. That are obviously, by definition, obviously concurrent at X. Right, so I'm just taking a triangle ABC, and I'm choosing any point x. Could be interior, could be exterior, just can't be on these sidelines. So just choose any old point x, and connect in AX, BX, and CX. Those are three Chevians. Two of them are exterior, but they're all concurrent at this point x. So what have we seen? We've seen that if we have three Chevians that are concurrent, then their isogonals are either concurrent or parallel. So we've seen that the isogonal Chevians are also then concurrent or possibly parallel. So in the case where the isogonals are concurrent, they're going to be concurrent at some point. Call it maybe a notation people usually use is x star. I don't think our textbook does this. But if they are concurrent at a point, say you call that point x star, we say, or we call, let's say, we say x star is the isogonal conjugate of x. So this is the definition of isogonal conjugates. I want to point out that don't think of this as starting with Chevians at all, right? I start with just this point. I start with just this point. Using that point, that defines three Chevians. And from those three Chevians, I look at their isogonals. It's possible those three isogonals are parallel, in which case I don't have anything interesting happening. But most of the time, my three Chevians, or my isogonal Chevians, will also be concurrent. They will be concurrent at some point. How does this work? I forget exactly how this works. It might also be out here as well. Here, my isogonal is going to live here, here. Actually, concurrency would have to happen somewhere out here. We'll talk about this next time, exactly where the isogonal conjugates live, but if I take the three isogonal conjugates, or isogonal Chevians, they're going to be concurrent at some point, if they're not parallel, and that point is the isogonal conjugate of the original. So there's the definition. Not all points have isogonal conjugates. For example, if you live on the sideline, isogonal conjugates aren't even defined. But what points am I guaranteed that I do have isogonal conjugates? Interior points, right? If I have an interior point, the three Chevians passing through that point are all interior Chevians. So their isogonals are also interior Chevians, and therefore are concurrent somewhere. So note that obviously all points interior to triangle ABC have isogonal conjugates. And for example, the median point is the isogonal conjugate of the centroid. example, this median point is the isogonal conjugate of the centroid. Is that clear? That's by definition of exactly how we define this median point. By our definition, by our construction, it should be completely clear that we started off with 3 medians. We took their isogonals and observed that those are concurrent at the symmedian point. Well, that means it's the isogonal conjugate. Some of our other points, we won't prove any of this, but some of our other points are similarly related. The in-center is pretty obviously, its isogonal conjugate is itself. In fact, it's the only point, interior point for which that's true. And the orthocenter and the circumcenter, those happen to be isogonal conjugates as well. But we won't prove that. So my question is, how long do we have? Just over 10 minutes. Under 10 minutes. My question is, which points actually have isogonal conjugates? As we've seen, all the interior points do. No points on the sidelines do, because they're not even defined. But what about the other points? So here's the question. Which points in the plane have isogonal conjugates? All right, we've seen all interior points do. No points on the sidelines do. They're not even defined, right? By our definition, they're not even defined. By the way, that's worth thinking about. You should think about what happens if you take a point on one of these sidelines, just take a point on the side of a triangle, and try to define its isogonal conjugate. See what issues you run into. It's a worthwhile exercise. So what about the others? Well, it's defined for all the others. As long as you're not on the sidelines, this definition is defined. So when wouldn't we have isogonal conjugates? Well, we're taking 3 Chebians, we're looking at their isogonals, and we're looking at a point of concurrence between them. So the only way I wouldn't have that my isogonal Chebians are concurrent is if they're parallel. So that's what we're looking for. So any points that give rise to 3 parallel isogonal Chebians. And it turns out that the points to do that are precisely the points on the circumcircle. But we'll talk about that next time, because we're running out of time here. And I'm stopping with this stuff a little bit early, because I wanted to discuss one of the homework problems, which I believe is 4A.3. 4A.3. Let's suppose I have a triangle. Suppose I have a triangle ABC. The question is, look at the points of tangency of the three x circles. So look at the points of tangency of the three x circles. Maybe I'll call them P, Q, and R. Why don't I go P, Q, and R? Not in this order. So let's go this way. P, Q, R. There we go. So P, Q, R, points of tangency. Of x circles. Obviously, those are too many words. Mathematicians are pretty lazy. I believe these are usually called x touch points. So the x touch points. And we want to show that if we draw on these Chevians, AP, BQ, and CR, they must be concurrent. How are you going to do that? You're going to use Cheva's theorem, and you're just going to compute the Chevian product and show. I've messed up my order, haven't I? My Chevian product, I usually have P over here. It doesn't really matter. Or is that right? No. We have R here. AR over RB, BP over PC times CQ over QA. We want to show that equals 1. How are you going to do that? Has anyone done this yet? Well, I need to know something about these distances, right? We did this for the Gergonne point already. We proved the Gergonne point exists, where we did basically the exact same problem, but we had the points of tangency of the in-circles, the so-called in-touch points. Right, so maybe these are the in-touch points right here. X, Y, and Z. And for the Gergonne point, we showed that for those guys, AX, the Chevian product, AX over XB times BY over YC times CZ over ZA equal to 1. And how did we do that? Do you remember how we did that? It was really easy. Proving the Gergonne point existed was super, super easy because for these points of tangency of the in-circle, we know these distances. Not only do I know the distances, but more importantly, I know how they relate to each other. For these points of tangency of the in-circle, I know, for example, AX equals AZ. All right, that's a true fact about these so-called in-touch points, the points of tangency of the in-circle, is that these distances, AX must equal AZ. Doesn't look like it in this picture, but AX equals ZA. What does that mean? That means that when I'm computing this product, those guys cancel. I also know BX equals BY, or XB equals BY, so those guys canceled. And I know YC must equal CZ. So those guys cancel. And therefore we had that the Chevian product was equal to 1. Does that ring you a bell? Do you remember doing this? Okay, so proving the Gergonne point existed was super easy because we just had to use these facts. I'd like to do something up here as well with the x circles. I need to sort of come up with relations between all of these distances. Do we know anything about these distances? So do I know anything about AR? Well, I actually do. This was the homework you just did, 2F.2. All right, 2F.2 was you have those two circles. You had a triangle with an in circle and an X circle. And what did you prove? You proved that AU was the same distance as BB. Okay, that was the homework you literally just did, which tells me something about, well, it's the distance from a vertex to the in-touch point, but that relates to the distance from a vertex to the X-touch point. So in this picture, what do I have? If I want AR, well, AR is the same as BX. Right, the distance from a vertex to the X-touch point is the same as the distance from the opposite vertex to the in-touch point. That was by 2F.2. What does BX equal? At this point, I'm almost doing the entire problem. Maybe I should stop here, but BX equals BY. And once again, invoke 2F.2. BY equals the distance from a vertex to the in-touch point is the distance from the opposite vertex to the X-touch point. That's CP. Or, as it's called in this ratio, PC. So those guys cancel. Do that for all of them. And then you're done. So difficult problem, but if you have 2F.2 to work with, which we do, there's the crux of the argument, use that and you'll be totally fine. And we're a few minutes over, so thanks for bearing with me.